Hi guys, I thought I'd just take some time to quickly explain to some of you the concept of a function and the notation that can be used. So just for your clarity, in this part of the video series, I'm still focusing on functions. There's still a lot to do, but we still have a lot of time, so that's fine. Now, a function is defined as a relationship. And this I wrote in my own words. A relationship that relates one set of numbers to another. More concisely, it means that it's a relationship describing the relationship between an input and an output. And what I mean by that is this x here in purple. That's known as the input, also known as a variable, and more particularly as an independent variable. Then you have this notation here, f. That can be a f or a g. That's the function name. And on the right here in mustard is typically the function that's defined, and that also gives you a number, and that's the output. Okay, so different forms. We can have a function of one input variable, and as I said, that's an input variable that can also be described as an independent variable. And in this case, in this notation, that's x. I can also write it randomly because that x is just a symbol, right? So it can also be written, for example, in terms of t. And then I can also just give that function a name. So in this example, I give it a name as y. So y equals t squared. It's still just a function of one independent variable, t. Then I can also name it z. Doesn't matter. And I can also then define a function z, for example, in terms of more than just one independent variable, right? So it can be, in this example, a function of r and s. If we think about the graphs then, if we have one input variable, we always have a two-dimensional graph with a function described as a line. So in the first example here, we have a parabola. And the second example, we have a straight line, just this t. So y equals t. Those are then functions for one input variable. And notice this independent variable is on the x-axis, and the dependent variable is on the y-axis. Okay, but we can, for example, also have a function that, in this example, I have a function that is determined by two independent variables, x and y. And in that case, we have a two-dimensional or three-dimensional graph. And this function output z, if we see that in terms of a graph, this is no longer just a line, but it's a surface, right? It's a flat surface in the x, y, z space. And obviously this can be scaled up. So you can have, for example, multiple dimensions. So let's say we're going to call this function z, defined by a function g. And that can be a function of, well, right, x, y, k, l, This then sort of reaches a realm where you can't really graphically represent it because we're limited on what we can think, right? We typically can think in terms of 2 dimensions, maybe 3, but after that we get limited. And then this function, this value will just put out a number. Some kind of number. We can't give that, as I said, it's hard to visually represent that or to even imagine that. But so a function, therefore, can depend on multiple independent variables. And as the number of independent variables increase, also so does the complexity of the function. So that's all I wanted to say to you. What that means in terms of the test then, or the exam, is if you get weird things here, don't get a fright if all your examples you did was in terms of x and y, and all of a sudden in the test you get a function as defined in terms of r and t. This doesn't matter. These are they're just basically symbolic placeholders for values that you will feed into the system or into the model. What their values are is important, but what symbol you use to represent them is quite trivial actually. But I know that some people get a fright if all of a sudden you always work from x and y, and then all of a sudden you get a function of r. People don't know what to do. That's all I wanted to say in terms of functions.